Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video starts a series of videos on vectors for a trig or pre-calculus course. Doesn't really matter. As long as you have some trig background, you can pretty much deal with any of these problems in vectors. So vectors are beautiful, and I, as an applied mathematician, love vectors because you can really do some great application problems with them. So let's talk about what a vector is. This video is dedicated to a geometric approach to vectors, which you need both that and an algebraic approach to really truly understand vectors. So in a way, we're going to be defining a whole new number system, and that makes it so important for us to basically agree on some basic definitions before we move forward. So some of the definitions are as follows. A scalar quantity is a quantity having magnitude but not direction. Well, that's pretty much any number you've been given so far in mathematics, like 3, that's a scalar, or pi, that's a scalar, or negative root 2, that's a scalar, 0 is a scalar, 1 is a scalar. Basically every number you have, half, 7/3, all that stuff. Those are scalars. They're just numbers. They don't give you a direction. They have magnitudes. For example, the magnitude of a negative root 2 is actually just a root 2. That's the size of the number. It's its distance from 0, if you will. That's kind of what a magnitude means. On the other hand, a vector quantity is a quantity that has both direction and magnitude. So it is kind of like a number, but it implies a direction as well. And because it implies a direction, you kind of immediately think of arrows, and that's exactly what we're going to be doing. We're going to have stuff like this going on. It has a length, so that length is called its magnitude, and it has a direction. And the direction usually is measured from the positive x-axis, or essentially the positive horizontal line. So it has a direction of theta and a magnitude, whatever the length of that vector is. That is a vector quantity. Notice I didn't write down a number because I don't want to. I really don't want to, honestly, because it'll just get confusing. For right now, we're going to do the geometric interpretation of vectors. And there's a lot of different, there's an infinite number of different vectors. So there's that vector right there, right? There's this vector right here. There's this vector right here, very long vector. If you've ever watched the news and a weather report, they give a vector field of winds within a vector or within a news report. And so you can always Google vector fields winds, and you can find these beautiful wavy vector fields for wind strength and direction. And that's actually a really good example, wind strength and direction. So at any point in a field, for example, so if you're out in a field and there's stalks of corn or something like that, if there's enough wind, that corn will bend. So you might have corn bending like this here. Maybe this one bends this way, this one bends this way, this one bends this way, that length, and so on and so forth. These indicate how strong the wind is and which direction the wind is going at that very moment. Okay. And so this is where a vector field can be very powerful, because not only does it give a direction, but it gives a magnitude of how strong that wind is. Now I drew those arrows, but I didn't really mention anything critical about them at the beginning there. So let's now start talking about the parts of a vector. So you have this vector like this, right? And I've always drawn them with a little dot at the beginning and then an arrow at the end to indicate which direction's heading. The initial point for a vector is the point the vector emanates from. So this would be the initial point. I'll just write that in there, initial point. And the terminal point, often designated with an arrowhead, is the point at which the vector ends. So this would be the terminal point here. Terminal point. There we go. And a lot of people will, you'll see these written as tail and head. So the terminal point is called the head of the vector, and the initial point is called the tail of the vector. I tend to not use the tail head language, mainly because that's not the way I learned it, but that's okay. You could use tail, head, all that fun stuff. But that's the definition of initial and terminal points for a vector. Let's see what else we have. We have the magnitude. Well, that's the geometric length of the vector. So again, as we wrote in the last screen, this might have a magnitude or a length of m. Well, this one, which is the opposite direction, looks to have the same magnitude. And in fact, this guy right here might have the same magnitude. So they could have different directions, but the same magnitude. It's just different lengths, or the same lengths, just different directions. That's all. But that's totally fine. Now let's start talking about how two vectors can be equal. Two vectors are said to be equal or equivalent if they have the same direction and the same magnitude. For example, and let me be somewhat accurate with this. So I'm going to bring out the big guns here. I'm going to create a vector that has an angle or a direction of 27 here, 27 degrees. So there we go. There's my vector right there. I'll call that vector. Well, I'll call that vector V. The notation we use, by the way, for vectors is this V with a arrow or a half arrow on it. That tells the world you're talking about a vector at that point. So that vector's name is V, and somebody comes along and they say, hey, I've got another vector and it's way down here and it looks like this. So because those two vectors have the same direction and I measured them out, the same magnitude, the same length, I'm almost positive they are. Yes, they are. Because those two vectors have the same magnitude and the same direction, those two vectors must be equivalent according to the definition. Now, if they were different directions by a single degree, or one was slightly larger than the other, they would not be equivalent. There you go. That's how you can define equivalency of vectors. Same direction, same length. There are an infinite number of vectors that are equivalent to this vector V. They all have the same length and they all go in the same direction. Then we have what's called the zero vector. The vector with magnitude 0 is called the zero vector. It looks like this. Not very fancy, right? It doesn't really go anywhere. And I've seen different definitions on this, but some people say it has no direction. Some people say that it has every direction. It really doesn't matter to me which one you think it is. All you need to know is it doesn't go anywhere. It has magnitude 0. It's just a point in space. Now, since we're in a math course, we have to start talking about mathematics. Specifically, we're going to start with what you started with when you had numbers. Addition. How do you add vectors? Well, this is going to be a geometric description of it. The result of the sum of two vectors, often called the resultant vector, is the vector with initial point at the initial point of the augend, which is the first vector, and the terminal point, or the head, at the terminal point of the addend, which is the second vector. By the way, the words augend and addend are not from vector arithmetic. They're actually from just arithmetic. When you add two numbers, the second number you're adding is called the addend. The first number is called the augend. Just kind of an interesting little fun fact. I like those every once in a while. So geometrically, let me just show you what I mean when I say the sum of two vectors is all this stuff. So let's just say that we have a vector. I'm going to draw them in two colors here. I'll draw the first one in black here. So I have a vector V. Okay. And to that, I want to add a different vector. Let's say we add a vector that looks like this. Let's make it somewhat long. And let's call this vector V and U. So this will be vector U. It's very common for people to use V and U's for vectors, just how it is. So let's say that you want to add u and v together. Well, you can either add v to u or u to v. It doesn't really matter, and I'll showcase that in a moment. But when you add them, the result, which is a vector called the resultant vector, will start at the initial point of the first vector and end at the terminal point of the second vector when these two vectors are placed together head to tail. Or yeah, head to tail. And which I didn't put, by the way, I didn't put in a definition. I apologize for that. So the definition should have had the additional piece of information that when you add two vectors, you glue them together head to tail. So let's say I'm taking v plus u. I'll glue them together like that. Hold on a second. I'm going to copy that u just in case I need it. And so we take v and u, we're going to add them up. And the sum of v and u is going to be a vector that starts at the initial point of v and ends at the terminal point of u. And let me see if I can get this done. There we go. That's the vector v plus u. You take v, you attach u to the head of v, it's head to tail addition. And the resultant vector starts at the initial part or the initial point of v and ends at the terminal point of u. And that is the geometric vector if you add v and u together. Well, what if instead you didn't want to add it that way, but instead you wanted to add it u plus v? Well, let's see how that works. So there I have extracted u and v. Let's go ahead and add it the other way. So I'm going to grab that u. I'll just move maybe down a little bit. Actually, I don't think I need to. I'll leave it right there. And I'll take that vector v. Remember, we're doing u plus v. So I'm going to attach v to the head of u there. So that's going to be u plus v. Let's go ahead and see what that measures out to be. I'm going to use green here. And you will see that u plus v, the vectors, that looks like the same vector as v plus u. And in fact, if I were to rope that up, let's see if I can grab this without grabbing everything else in the world. You can see that that vector is basically the same as the vector u plus v. V plus u and u plus v are the same. So there you go. That's a pretty good manipulation there. All right, so that's how vector addition is done. And I've made the mention here that u plus v requires a terminal point of u to attach to the initial point of v. For example, there's u plus v was happening right here. So the terminal point of u attached to the initial point of v. So that's just, and I didn't draw the arrowhead on that, but there you go. So that's what I mean when you, by tail to head or head to tail addition, is that you attach the head of the first to the tail of the second, essentially. All right, so that's geometric addition of vectors. By the way, you can add a lot of vectors this way. In fact, since we're here, we might as well just do it. So let's suppose that you wanted to add maybe 4 different vectors. So here we have v, u, w, and r. And let's suppose that we want to just add it this way. Let's go ahead and say we want to know what, I don't know, r plus v plus w plus u are. By the way, you might be wondering, how does subtraction work? And that's something we'll talk about in a different video, but I will go ahead and just say right now that the when you take the opposite of a vector, it just switches directions. Or sorry, yeah, it switches facings. So the initial point would become the terminal point, and the terminal point would become the initial point. So it'd look like this here. Okay, so that's would be the negative of u. Okay, trying to erase that. There we go. All right, so let's go ahead and take r, add v, and then w, and then u. So I'm going to take r here. I'm going to give myself some room, so I'm just going to grab r here and move it off over here. And we'll take v and add that to it. There we go, something like that. And then we'll add W to that. And then finally, oh, remember U had this direction to it. Sorry about that. And finally, add U to that. So grabbing U and adding U to that. So there you go. Now that summation will be a brand new vector that starts at the initial point of the first vector and ends at the terminal point of the last vector. So again, let me zoom out here and grab my ruler. It'll start at the initial point of R and end at the terminal point of U. Let's see if I could do this. And I don't really have a great color to use. I'll use orange, even though this is going to be really large, I think. Actually, that worked out kind of nicely. And I will turn off the ruler. I'll zoom in here and I'll just put a little arrowhead there. That is the vector R plus V plus W plus U. R plus V plus W plus U. These are very powerful in physics because you're really dealing with forces, and you might have all these forces acting on some object, and one force pulling the object this way, one force pushing the object that way with that amount of strength, another force moving the object this way with that amount of strength, and the final force moving this way with a bunch of strength, right? The resultant force, basically the result of all those forces acting, is this orange vector. The result of all those pushes and pulls and everything would be that the object is going to move this way with this level of magnitude, whatever that may mean in that situation. Okay. Now that we've dealt with vector addition, and I've talked briefly about like, well, what if it's subtraction? We're not really dealing with that here, but at least we dealt with vector addition. Let's talk about multiplication. Now, vector multiplication is not something we're going to talk about in this video series because that is not well defined, really. But scalar multiplication is. Scalar multiplication is very well defined. The result of the product of a scalar C, remember a scalar is just a number, and a vector is the vector, absolute value of C times the magnitude of the original vector. If C was negative, then the resultant vector is opposite in the direction of the original vector. So let me give you an example here just to kind of cement that statement. Here's a vector V, and it looks to be about 1 inch in length, or 2 inches in length there. Okay, so and it's at an angle of 24 degrees. All right, let's go ahead and see what the vector negative 3/2 V looks like. Well, it's going to be the same vector. It's just in magnitude 3/2 the size. In other words, 1.5 times as big. So if this was a length of 2, 1.5 times that size is a length of 3. So I'll have a vector of length 3. Let me go ahead and draw that blue vector in. I'll start up here. 1, 2, and 3. So there's my vector of length 3. So far, I have right now 3/2 V. I want it to be negative though, which means it'll just point in the opposite direction. There you go. That is actually negative 3/2 V because again, V was of length 2, and I want something 3/2 that size. So 3/2 times 2 is 3. So there's 3. Like the 3 right there, and I need it to be in the opposite direction. That's it. Again, I said that I try to bullet those in there as initial points, but there you go. So that's how scalar multiplication is done. If you multiplied a vector by 0, it would become the 0 vector. And as I mentioned before, vectors are most often used in physics courses and in physics and engineering, really. So there's a website here. It's been around for a very long time, fallstad.com, and there's an applet there that I've always found very helpful. So I'm going to hop over there and just describe a few things. So what you see right here is sort of like a black hole or a sinkhole or something like that. And you have all these particles moving to the center. Notice they're moving faster as they get toward the center. It's because they're being sucked in there. You can see they just move faster and faster as you move toward the center. You can represent that movement and the direction the particles are moving via a field of vectors. And so you can see the top down. So this person has it to where they use color to show the field strength. Most people would use actual vector lengths. So that's something that I don't like about this. However, it's still very nice to kind of see these. Let's see if I can do something slightly different. So this is the velocity vectors. Let's try something different here. So here you have like a rotational field, and I want to take a look at the vectors, the field vectors here. So let's go ahead and just see that. Again, the way this person has coded this, they use color to denote the strength of the vector. And so that is, the lighter the color, the stronger the vector. Normally we'd use vector lengths here, so that's a kind of a disappointment, but still very cool. You can kind of see this. And now I'm just having fun. This is a Lorentz attractor. And so it almost looks like, if you go around here, it almost looks like intersecting galaxies. That's a Lorentz attractor. And let's go ahead and again just display the field vectors so that we can see them. Now in this case, man, you can see at least the vectors show the direction. Unfortunately, they're not showing the magnitude, but still super awesome stuff there. I know that it doesn't have the length of the vectors, but I hope that at least it shows you some cool stuff going on there. That's pretty awesome.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.